Well, welcome back to the Old Iron Lever channel. Bob here, and today's video we're going to revisit a project we did a while back. I had some friends that needed their Maytag washer repaired. That was the bearings, tub bearings were going out, and looked a little bit on what's required and all that, and it looked like a special puller was required. So looked online, and you could buy them for $400 or whatever. And I was in kind of a hurry, so I thought I'd just knock one out real quick. And they had a lathe, they had some mild steel and nuts and bolts and things. So I made a forcing screw and some plates. Let me grab a couple of those plates. So we have a cup here that basically is, when you're pulling a bearing out of the tub, it seats into here. This is the relief for it to come out of the tub. Then on the other end of the puller is different size little washers. The ID that fits in, the OD of the small part fits in the ID of the bearing, and the big part hits the outside of the bearing and pulls it into place. Anyway, so I got done with this project and I fixed their washing machine. And the guy, the husband of the pair, is a well-known chef in our area. And so we got some really nice home-cooked meals. So anyway, let everything kind of move forward now. And I got a question on the comment section of that video if I had any of these, if I made these pullers for sale. I said, well, no, not really. I just made this one because I needed it. I really don't need it anymore. And, do you want to buy it? And the guy says, well, yeah. So we settled on a price, and I sold him the puller. Now, remember, I built this thing as a one-off. It's just to get the job done, and then whatever happened out of it. As far as I was concerned, after that, it was I'll hang on to it for the next time I need to do one. Probably never. And other than that, it's just steel hanging around the shop waiting to be used for something else. So the fellow that got it from me said it worked great. He was able to pull all the bearings out, and he put one of the bearings in. When he put the last bearing in, I don't know the exact situation, how hard he was gronking on the bolt or anything, but it broke. And he said it was fine because he was able to hammer the bearing in, and I thought, well, that's not perfect, but okay. Anyway, so he asked if I could make him a stronger forcing screw, and we went back and forth about what we should change on it, and so we wound up making several changes. His bearings were apparently slightly smaller ID than mine were, and so I actually had to come and turn this diameter out on a couple of these to get it where it would fit smoothly in the bearing. I don't know why, but if that was the case, then it's possible, as it was sitting in here, if it didn't seat squarely into the bearing, then it's possible it got cocked a little bit, and when you put some pressure on it with it sitting like that, it could snap it off. On the other hand, I didn't really do any strength calculations or any expectations that I would need to use it again. So I did a little bit of figuring, and the thread that was on there was a 1/2 inch 13 thread. The thread we decided on putting on the new one is going to be a 5/8 11 thread, and the rod itself is a fine thread. It's a 3/4 16. So what can I do? Well, one of the things to do, go up to 5/8 of an inch. The minor diameter of the threads, which is really what you're looking at, is the cross section from root to root. At the diameter at the root for calculating the strength of the thing. So 0.41 works out to 0.13 square inches. A 5/8 is 0.52 or 0.21 square inches area, which is 60% bigger the area, cross-sectional area is 60% bigger. So already we're going to get 60% more strength. And I went from, instead of just turning some threads on a grade 5 piece of mild steel, I got some grade 8 pre-threaded rod. And looking at the yield strengths, now there's two strengths to consider, two basic strengths to consider on a fastener or anything you're going to put a tensile load on. Grade 5, the yield strength is 92,000 pounds per square inch. Grade 8 yield strength is 130,000 pounds per square inch. So grade 8 is 40% stronger than grade 5. Now I use the yield strength. That's the point at which the steel starts stretching permanently. You have an elastic limit as to far as how far it will stretch and then recover to the same length again. Once you pass the yield strength, then you'll stretch it out and it won't all recover. It may mostly recover, maybe little recover. But once you pass the yield strength, the threads don't fit right anymore. There's things that can happen. It's been stressed. If you look at the tensile strength, that's the strength at which the thing breaks off. And that's 150,000 for a grade 8 and 125, I think it is, for a grade 5. So still, it's quite a bit different. But that's the point at which the wince falls off the bumper on the truck. But in our case, we're interested in the yield strength. So, and just for completeness, I also calculated what the grade 8 strength of the 3/4 16 threaded bolt is, the main forcing screw. The minor diameter is 0.66, area is 0.34. It is 63% stronger than the 5/8 grade 8. So we put all the numbers to it. We multiply the pounds per square inch of yield strength and the square inches of usable diameter. The 1/2 inch had a tensile yield strength of about 12,000 pounds. Seems like a lot, but when you got a fine threaded screw and you're really gronking on the end of it to crank it, you can put a lot of pressure on it. The 5/8 grade 8 is about 27,000 pounds. So that's quite a bit bigger, quite a bit more. It's over twice the strength of the grade 5. So my fix here, I have confidence, will be much, much stronger. And just by comparison, the 3/4 grade 8, which is the main part of the forcing screw, is 44,000 pounds. So clearly this piece is going to break long before this piece is even going to yield. So anyway, and just for those of you who are new to this, the minor diameter is the distance between the root of the thread from one side to the other on a bolt, on a threaded fastener. And the minor diameter for a external thread is slightly different than the minor diameter for an internal thread. For our purposes, that really isn't very important. So the decision was made, we're going to go to a 5/8 grade 8 thread. And we made some other changes too. One of the things, as I mentioned, I made these things fit better. On the cup and the forcing screw, I bored the cup out. That used to have a grade 5 nut welded to it, which worked fine. That didn't yield. And then I've got a grade 5 coupling nut, which is quite a bit longer than a standard nut. Let me grab the full regular coupling nut here. So there's there's probably almost 4 times the length. So I am going to weld this in, and the reason I picked a grade 5 and a coupling nut was that if I weld on a grade 8 bolt, if I were to put a grade 8 nut in here and weld it into place, the odds are I'm going to lose a great deal of the strength out of this bolt or this nut. The grade 5, I'm going to lose some of the strength, but when I weld it, I'm going to have a weld down here, and I'm still going to have all this material that'll give me the strength. And but even this little piece here is twice as long as a standard bolt or nut. And So I'm going to have twice as much material putting pressure on this. And I think that's going to be a lot better. And the other change I'm making is on this end, I'm going to put a coupling nut and weld it on the end. So again, we have much more thread engaging the nut. I'm not too worried about the weld breaking. It didn't break last time, and I don't think it will this time. I'll have to bore these out for the new 5/8 size hole. I think there's another one or two over there anyway. So anyway, that's the project, is make a new forcing screw with a 5/8 thread on it. And so this is a left thread because when you go to tighten this screw up, you've got this arrangement sitting here, you're tightening this up, it's putting quite a stretch on these things here. And there's a nut on the bottom side. Well, what we want to do is keep that from unscrewing the nut that's on the back of this thing. So it's like so. So if we make it left thread, it will tend to tighten it, if anything. So that was pretty much the nature of the modifications we're going to make today. The other thing is, operationally, I'm going to just remind the guy that I'm building these for, is it wouldn't hurt to lubricate those threads. And I put a little EP grease on it, or some oil, but something to take out some of the well, I guess you'd call them galling forces on the threads, the contact between the thread and the nut and the thread on the bolt. So without further ado, I guess we'll get into it and get on the lathe. We're going to cut this to size. I'm going to make it slightly longer than it was, due to the fact that I have much longer things to accommodate, and I don't remember how much space there was left over in here. So I'm going to make sure that I don't compromise, by making it too short, making it difficult to use. Okay, we're getting ready to machine the forcing screw, and it's just a piece of 3/8 fine threaded rod. It's a grade 8 rod, and the first operation we're going to do is just bevel the back end of it. This is where the big nut that we weld into the end of it will be used, or will be installed, and the bevel here is just to give me a nice V for the welding. Okay, there's that. I'm going to turn it around, and we're going to turn down the other end to 5/8 of an inch diameter, so we can make the 5/8 coarse left-handed thread. Putting aluminum pieces in here to protect the threads from the vice jaws. Now, I originally had cut this back 2 1/4 inches, but I really don't need to go quite that far. The nut and the thickness of all the pusher plates are the same thickness. Is quite a bit less than that, so I'm going to give that a quick measurement. So right at 1 inch, so I'm thinking 1.5 inches would be plenty. Give us some extra thread and all that. So my turning tool, D&MG tool, and I'm going to go 1.5 inch on dial calipers, and we'll set the travel dial where we want it to end. That's very close right there. Set the travel dial here. That'll be my stopping point. Come in here and touch off. Zero my crossfeed dial. Okay, and we're going to want to come off 1/8 of an inch on diameter, 1/16 of an inch on the side, which is 60 thousandths. I'm going to take off about 40 and give ourselves a measurement and see how we're doing. There's a fair amount of spring in this stuff. You wouldn't think it would be the 5/8 bolt, but it actually has a lot of spring. I might have to do everything with spring passes before I measure. Now what I'm going to do is I'll turn this down to the major diameter of the threads. Then I'm going to single point it for a while just to get the worst of the metal hogged off. And then I'm going to come back with a die and clean it up with the nice clean, even threads. Let's stop there and take a quick measurement, see where we're at. We're going to be at 625, and we are at, clean the dial calipers, we're zeroed. We're at, right, 660, call it. So 25, I got 35 to go. Take 15 cut the most. Let's see, 15 will give me 30. This stuff is pretty springy, so I think I'm going to take a 10 cut. You may see me at the end of each cut whenever I'm doing something like this to reset the dial, the crossfeed dial. And what I'm doing is I'm setting it right back where it was before I backed out. That's just a memory device for me because, quite frankly, I may not remember from 1 second to the next what I was doing. I'm going to take a spring cap pass on this too. See, they're taking a couple thousandths off of that. Like where I was. Okay, we are at 639. So we got 14 to go. 7 on a side will give me, let's see, 639, 20, yeah, 7 on a side. I'm going to go 5. And then I will spring cut, check, spring cut, check. See what happens. Okay, we should be getting within a couple thousandths or so. 628. So I need to take 3 thousandths. I'm going to dial it in 1 more thousandth and speed up my rotation here. That should get me very close to the final diameter. .626, 626, 626. I need to take just another shave off of it. Okay, 625, 625, 625, we're good. Okay, now we're going to single point this, and there's more than one technique you can use. Now, first and foremost, I want to make sure I'm clamped down really good, because I don't want it slipping. If it slips, I lose my timing for my cut and all that. Go get this thread done. Now, there are many ways to do this. The way I'm going to do it is I have my travel dial set at 0, and that's where my starting point of my threads is going to be. I'm going to thread outward. I've reversed the lead screw speed or direction, so instead of advancing this way, it advances that way. Yeah. Okay, so I'm at 0. My compound's at 0, and I've touched off at 0 here, like so. Each time I come back, I'm going to advance the compound with everything else set to 0. I'm in back gear, by the way, too. I'm in back gear only because it makes it easier to hit the number on the dial. Back it up. Back to my travel dial being on 0. Take this back to 0. Advance 5 thousandths. Watch for a line to come by. And there we go. Okay, I've got my thread about as far as I want to go. I want to take the last little bit with the die, because I'll get a more even, take the spring out of it, and I'll get a better finish on it. So I am going to stop and chamfer it. All right, once I take it out, then I'm done. I can't put it back in and use the single point method anymore. So everything will be out of time then. Okay, got a little anchor lube on it. We're going to give it a finishing pass with the dye here. This takes enough work doing this after it's already been roughed in. Be a lot more work if we were cutting threads from bare stock to begin with. Put a little more lube on it. So the cutting's out of the way. Okay, that's about the end of where the threads were. Put a test nut on it and see how it works. Nice fit. Grab a wire brush. Okay, any of the trash that's in the thread should be gone. Let's see if that gets us. Still a little, I guess, still usable down on the end here. I grab a 15/16 and spin that on a little further. I'm going to have to run it down another time or two here. There we go. That'll do it. Okay, that's two of the nuts shortened. Okay, shorten it by that much, and then I'll turn it. I like that. That's where I want my stop to be. And I take it down to 1 36/1000. If I can read with this one or not, but yeah, I can go a little over it. Inch 021. Did I make it too small already? Not much, but it's fine. Quit there. Okay, the next step's going to be to set up to weld it. That's going to be a pretty good fit there. Okay, we've got everything turned down to the right size. I need to put a little relieving cut in here so that when we're pushing the bearing with the outer race, the inner race isn't being pushed on. We're going to be pushing just on the outer race. So the way I did that in the past was with sort of like a trepanning cut, only I'm not square on both sides. So I'm going to come in here, get out of the way. Well, this is just an eyeball cut, just relief. Okay. Now we're going to chamfer these edges. They don't need to be hard chamfer, just a little bit. Now we're going to part it off, which will be a trick. That's a huge part off. All right, we got a little bit of lathe work left on one of the discs. This is the one that was originally a ductile iron. I decided to make a new one out of steel. Just need to face it off, bevel the edge, and drill a 5/8 hole through the middle of it. Here's the finished kit. This is actually complete except for a little tube, that's a spacer tube that sits between the bearings. Anyway, there's the two forcing screws, and you can see the weld doesn't look too bad on these. One of them is a little longer than the other, won't make much difference. The cup and the old ductile iron pusher, and then the replacement are made out of steel, and big bearing, a little bit of bearing things, and some left hand nuts, and that's about all there is to it. Well, as always, thanks for watching, and thanks for subscribing. If you would like to leave a comment you think I'd like to hear, well, please feel free to do that. And until the next time, happy trails.